Hello and welcome back to Abstract Linear Algebra, the video series where we continue discussing topics from linear algebra in a general sense. And in today's part 28, we will talk about so-called equivalent matrices. This notion is related to the matrix representations of linear maps that we have discussed in the last video. However, as always, before we go into the details, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, with the link in the description, you can download additional material for the videos. Okay, with that, let's immediately start with a fact that we have learned in the last video. Namely, we have seen two 3x4 matrices that are different but still are related in some sense. And this relation we have explicitly calculated in the last video, because there we have shown that they both represent the same linear map. More precisely, it was the linear map from the polynomial space P3 to the polynomial space P2, which was given as the derivative. And now the reason that we can get two different matrices as matrix representations for this linear map is that we can choose different bases on the polynomial spaces. Hence, what we get here is that we have two different matrices, but they are still related in the sense stated here. Therefore, one direct question we could have is, can we see this relation in the two matrices? Or to say it in other words, if I give you a third matrix, can you decide if this is a matrix representation of this linear map or not? And of course, we can also state this question in more generality, so we take any linear map between two vector spaces V and W. And then let's say we have a matrix A, which is a matrix representation of this linear map. And this representation is with respect to a basis B of V and a basis C of W. And if the dimension of V is n and the dimension of W is m, we have an m times n matrix here. And now let's say we just choose another m times n matrix, which we call A tilde. So for example, A tilde could look much nicer than A, which means it could have more zeros in the matrix. Then it often would be easier to calculate with A tilde as the matrix representation. Therefore, the natural question is, can we even choose A tilde as a matrix representation? Which means, can we find new bases such that the change of basis brings us to the new matrix A tilde? So this is the question we want to answer, and we already know in general the answer would be no, because, for example, the zero matrix will never represent this linear map here. However, in some cases the answer will be yes, and then we call the two matrices equivalent. So there you see, this already explains the new term equivalent matrices. And if we think a little bit about this requirement here, then we see that we can also remove L from this question. And the best way to see that is to look at the picture of the change of basis. So let's say here on the left hand side we have Fn with the standard basis, which represents V with respect to the basis B. And the similar thing we have on the right hand side, where we have Fm, which represents W with respect to the basis C. This means our first matrix representation we have here acts from the left hand side to the right hand side. And with the names from above, this will be exactly our matrix A. However, now we also know that our concrete vector spaces can represent the general ones with respect to different bases. Hence, changing a basis on this level is always given with an invertible matrix called the change of basis matrix. So this is really important. The matrices here in the middle are always square matrices and invertible. Moreover, we also see that every invertible matrix can act as a change of basis matrix. This means if I give you any invertible matrix here, then you can find a suitable basis B tilde of V. And a similar thing we can do on the right hand side for W, and then we find our new matrix representation. Hence, our conclusion here is that equivalent matrices are just connected by invertible matrices. So this leads us to the general definition where we don't need the linear map L anymore. But of course, the new definition will still tell us how we can find new matrix representations for the given linear map. This definition is just easier to read because only matrices are involved. And I would say let's use the same names as before, so an M times N matrix A tilde is equivalent to a matrix A if the shape is the same and they are connected by invertible matrices. So we have two square matrices and let's call them S and T. So the one is of size M times M and the other one of size N times N. And then we have the equation that A tilde is equal to S times A times T. And if you read it from right to left, you see we have exactly the thing in the picture. And this is the correct definition for the new term equivalence for matrices. And often it's worth it to introduce a new symbol for that. And indeed, often one uses the tilde symbol as a relation symbol. So not a special symbol, and you have to know what it means in this context of matrices. In fact, what we can show now is that the equivalence of matrices is an equivalence relation. In other words, the chosen symbol with a tilde makes sense. Simply because this is the common symbol one chooses to denote an equivalence relation. So in our case, this defines an equivalence relation on the set of matrices of the same size. And please recall, this means that we have exactly three properties for it. First, it's reflexive, which means a matrix is always equivalent to itself. And this is easy to show because one can simply choose identity matrices in this equation. Indeed, identity matrices are invertible matrices, so they are allowed in this equation. In addition to that, we also have a symmetry property, which simply means that the right-hand side and the left-hand side have no difference in the equivalence. So if A is equivalent to B, then this implies that B is also equivalent to A. Also, this property is easy to see because if we have this equality here, we can just multiply the inverses of S and T to the left-hand side. And then we immediately have the equivalence for the other direction. And now finally, an equivalence relation also has to be transitive. It simply tells us if we know two equivalences, then we can imply a third one. More precisely, if we have that A is equivalent to B, but we also know that B is equivalent to C, then A has to be equivalent to C as well. So this is exactly what transitive means. In fact, this property is also not hard to prove at all because one simply has to put invertible matrices together. So the whole thing is a good quick exercise to check your knowledge about invertible matrices. Okay, and now please don't forget, an equivalence relation always implies that we can partition the set into equivalence classes. And now in this video we have learned that two matrices in different equivalence classes cannot represent the same linear map. And I would say, in the next video I show you how we can characterize these equivalence classes. In fact, we have already seen this simple ingredient that tells us if two matrices are equivalent. However, this is something for the next video. So I really hope I meet you there and have a nice day. Bye bye.